Right. Good afternoon, everyone. I'm going to present the possibility of using the triangle derived from a tie-mounted single tie-mounted IMU for the purpose of gate phase recognition. This is my outline. I'll first speak about the Curtin University's wayfinding project, what it is, and as this work is a part of that project, and the importance of gate phase identification in these applications, wayfinding and other applications, and the gate phases that we have. There are several gate phases in the gate cycle, and then the existing techniques to detect gate or identify gate phases in real-time and non-real-time applications, and then the proposed technique, proposed approach, and gate phases that we could identify in that waveform, and the future work, and finally the conclusion of this presentation. And this is an overview of the wayfinding project, where we have a chest-mounted processing unit which has cameras, probably stereoscopic, which does stereoscopic image processing for the purpose of identification of cartridges, obstacles, doors, and so on. And we will be using a mobile phone, a smartphone, as the human-computer interface with audible feedback, voice instructions, as well as haptic feedback, and an IMU device or a processing device for the purpose of gait analysis. And all these devices will communicate with this main unit, and the smartphone will be used to communicate with the peers as well, because there may be many people many vision impaired people in this in the particular environment that we are considering. So anything that one person discovers can be shared with the others, and that is the overview. And my work in that is the gait analysis part, and this work presented in this presentation is a part of that gait analysis research. And gate identification and gate phase identification is important in many applications like indoor navigation, especially when it comes to vision impaired people, and of course healthcare activities like fall detection and so on, recovery identification, all those applications. And existing real-time gate phase detection systems are not very convenient in two ways. I will show you in later phases of this presentation. There are two main approaches. One is non-real-time, which uses huge equipment, and the others are also, of course, the techniques that people are using at the moment are not as convenient as dropping something into your pocket. Then the gate pattern. Another thing that we are considering is the gate pattern, and it may be different from a general user, a non-vision impaired user, to a vision impaired user, and with different types of chain usages as well. To illustrate that, here is a simple sketch where different techniques of chain usages are used. They are used in different applications, of course, different situations, but there are three different types. One is the 2-point touch, where you tap and tap, and the other one, the second method, is constant touch, where you sweep over the ground, and the third is a mix of that, which is tap and sweep. In one point you tap, one end you tap, and then the other end you sweep. Each of these methods have different usages. So generally, a person would use mix of these. So that, of course, we'll have to. That is one concern that we had in this work. If I switch to gait phases, there are two main gait phases where the first phase is the stance, where the particular leg in consideration, or the reference leg, is in touch with the ground, and the other phase, swing, where the reference leg is in swing. There are certain areas where both the legs will be in touch with the ground in sort of stance phase. We will look at those later on. There are sub phases, 8 altogether, 8 sub phases, 3 sub stance phases, and 3 swing phases. Now, as you can see in this diagram, the list is here, but I'll explain using this one. The initial contact is where the reference leg touches the ground for the first time. The heel touches the ground for the first time. That is the point. That is the initial contact point. Then during loading response, during the swing, of course, the reference leg is moving above the ground. It's swinging. So it's one limb support, a single limb support. The other leg is supporting your body weight. And initial contact point is the beginning of double support phases. And during the loading response, it starts beginning to transfer the load to the reference leg. And by the end of loading response, the full body weight is transferred to the reference leg. Then the other leg starts swinging. And mid stance, as you can see there, the other leg sort of moving halfway towards halfway forward, and the reference leg also from the forward position it starts to sort of a vertical position, and the terminal stance is where it moves forward further, and free swing is where the heel starts moving away from the ground, supporting on the toes. I'm talking about the reference leg. So all these pictures, the two pictures are the beginning and the end, except the initial contact where it's just a point, where the heel touches the ground. Then the swing phases, that's also divided into three sub-phases: initial, mid-swing, and the swing. It's again, as you can see there, with reference to the other leg as well. And according to literature, the percentages of the time of each phase with respect to the total gait cycle is shown in that table. This was used to confirm our result, of course, the waveform that we are picking the correct areas of the waveform. And we may relate the phases of one leg, or the reference leg, with the phases of other legs, as you can see in this diagram as well as here. The initial contact point of the reference leg is the beginning of the free swing of the other leg. Likewise, each phase of a particular leg matches or has a corresponding phase of the other leg as well. So in that case, if you detect or identify the phases of a particular leg, you may predict the phases of the other leg as well. The existing gait phase detection techniques. We have motion analysis systems which are optically based, but they are laboratory environment they provide laboratory environment for gait analysis for all the sort of physical health science purposes and so on. They have many reflectors and many cameras around the environment, and it takes more time for them to calibrate it. And anyway, they can be used at sort of moving environments or outdoor environments, indoor environments in real-time applications. Well, they are accurate, but expensive and limited to laboratory experiments only. And that means that you can use them in real-time applications. The inertial sensor-based techniques, many people are using inertial sensors in conjunction with others. As you can see there, that sort of arrangement, many sensors tied up to the leg or maybe to the foot, shoe, sole, like many sensors. Most of them they use sole sensors as well to detect the touching point, whether basically to heel contact or the initial contact point and loading response. They can easily detect by using pressure sensors attached to the sole. And of course, they need several sensors, not just a single sensor. Single sensor means single unit, but several sensors attached to the legs and the sole. And most existing work I found, they have done offline processing to recognize the particular phases, and the number of subphases that they have detected was limited to initial contact point, stance, and swing. They could detect whether it is on swing because none of these sensors would read the pressure. And the initial contact, because they have a sensor attached to the heel, just under the heel, so they can detect the initial contact point. And if both, if all the sensors give a pressure reading, that means that the leg is in stance. But they could not detect the other subphases in any means. All the papers that I have read, they could not detect all the other subphases. And the work proposed here, the gait face recognition based on triangle. The experimental setup, the IMU, a single IMU, a 9-axis IMU which has accelerometer, gyroscope, a triple-axis accelerometer, triple-axis gyroscope, and a triple-axis magnetometer was placed in the pocket freely, but upright position, so that we know that it's oriented in that way, so that its y-axis is aligned with the vertical direction of the leg, and x-axis perpendicular to the side, and z facing perpendicular outward. And that means gyroscopic x-axis reads the swing of the thigh. We did that because we wanted a minimum amount of computations to be done. And the thigh angle was calculated by fusing the gyroscope and the accelerometer, because if you get the angle purely based on the accelerometer, as the accelerometer reads the gravity plus any acceleration that the thigh has or the IMU has, the reading is not accurate when it is moving. So, on the other hand, if you keep on integrating the gyroscope to get the angle, get the position, the error in the gyroscope will be accumulated so that you will get a drift. You get the correct shape, but you will get a drift. So what I did was, when there is minimum motion I use the accelerometer only to get a correction. Do a correction, then keep on integrating the gyroscope, because integrating the gyroscope is more accurate than deriving the angle from the accelerometer. But it will introduce a drift. So to avoid that, what I did was, whenever the motion is less, very small, I'm using the accelerometer to calculate the angle. Do a correction and then keep on integrating. And this is a graph of the thigh movement. Starting from the initial contact point, this phase where you have this maximum is the initial contact point where the leg is at the forwardmost position. The reference is at the forwardmost position, and then during the loading response, it troubles somewhere in that area, and this point from the initial contact to the loading response is that period, and the mid stance until it crosses the 0 point, becomes vertical and then goes backwards. The angle is negative. So positive angles means forward movement, negative angles means backward movement. And this negative peak is the end of the terminal swing, terminal stance rather. And during the mid swing, the leg moves, the particular leg moves again, the thigh moves again towards the positive direction and becomes almost 0. And then the swing phase. Of course, during the swing phase, we could not recognize the initial swing, mid swing, and the terminal swing. Those three phases could not be recognized because it's in swing. And we notice these gradient changes in these two phases, where this is the break point between the mid stance and the terminal stance, and this is the end of the pre-swing, and it's basically pre-swing and swing phase break point. And as you can see here, from this waveform, we could recognize 5 phases out of the different out of the 8 phases. And we captured data from vision impaired people as well, and this darker one is for the vision impaired person, and the light one is for the non-vision impaired person. They look more or less the same, but at some point, as you can see there, this gradient change is not observed there, neither in here as well. But still, the main shape, apart from those gradient changes, the main shape of the thigh angle remains almost unchanged. But still, as we did not get many readings from the vision impaired person, we did not have sufficient number of data to establish sort of a point that it's either same or it's different. But still, we'll have to investigate that part, whether we can, based on the same waveform, or it's different. As future work, now this is just sort of illustrative approach, but we'll have to model that waveform and go ahead with detecting phase in an algorithm and in real time, and compare this result with we are planning to do an experiment with the collaboration of with physiotherapy people, and they have this optical based lab where we are going to compare the IMU based results with the optical based results and see if they are accurate enough to do these analysis. And in this case, the vision impaired person was using the white chain. And there may be other applications as well where the vision impaired person uses the guide dog or different styles of white chain usages. So we'll have to look at the differences or similarities between all these different applications. In this case, we will be looking at we will be comparing in this case means the optical based lab. We will be comparing the usage of different types of white chain with the guide dog. All these different techniques will be compared among. And in the same time, we will be looking at the time movement differences or similarities with different types of footwear, like thorns, high heels maybe, or boots, or sports shoes. May or may not be different, but we will be looking at that aspect as well. But we may be restricting the different types of footwear to the types that vision impaired. I mean, we can employ vision impaired people and see the differences of the time movement with different types of footwear usage, and of course different styles of white chain usages like two-point touch, constant touch, and the other one. So we will be doing that in the future. Right. As a conclusion, the possibility of detecting the gait phases based on the triangle derived by a single IMU, a single time-mounted IMU was presented in here, and 6 phases out of 8. Yeah, 6 equals 6. I was confused with 5. 6 phases, starting with all the 5 phases of the stance was detected, and the swing phase. So altogether 6 out of 8 were identified, and this approach has significant potential in using gait phase detection for the purpose of pedestrian navigation. So that's it, and thank you very much. Any questions? Yep. For the moment, it's not moving, but people are at the moment studying the movement of, not us. I read several papers of where people are looking at the movement in the pocket, but for the moment, it's not moving. Yeah, fixed. So the orientation is fixed compared with the time. Yes. Sort of firmly fitted in the pocket with a tennis. So very less. I mean, I can't say there is no movement at all, but the movement is very minimal, so we can neglect that. Sorry? Yeah. Okay, right. So, of course, this was done in, we collected several samples, and this waveform was observed in almost all the samples. Yeah. Right. Yeah. Yes. Right. Right? Okay. Yeah. The last one I did not get. Yeah. Yes. Right. Yeah. Yes. Yeah. Yeah. Yes. Right. 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 Yeah. Thanks. Yeah.
There's an assumption here that when we walk, it's perfectly symmetrical. But suddenly in the case of analyze is not beginning like the other way look is straight. And I thought that's the assumption. Nature behavior and the assumption. But in that case, I mean,
No.
something that can still see the behavior of different injury, it's obvious that they're not
Yeah.
but for first individual, this is a fair assumption to say that it's symmetrical.
Fairly equal, but not 100%.
Not identical.
Yes. Not identical. Yeah. I mean, well, that's true. That's true. However, like the model that I am planning is like sort of inverted pendulum model that people are already using for the to model the movement of the leg. And in that case, if you know the movement of one leg, you basically know where you are going because it's going like that all the time. So it's the movement of a single leg. Only if you have a step from the other leg to terminate or to begin with, there will be a certain error if it is not identical. But otherwise, for the continuous walk, if you just forget about the other leg and keep on looking at the steps of the particular leg, that should be enough. Yeah. Yes.
How would your system distinguish between I assume that you practice walking on a straight line.
Right.
What happens if you are walking in circles, the guy who's got the sense of the hand that change of direction.
Right.
Is there a way to distinguish changing the gait in the straight line or is it going on changing the direction?
Not at the moment if you are going in a short circle. But general walking, I mean, most of general walking, either you turn, very rarely you go in a shorter circle. I mean, a very small circle, but generally you will be walking on a deep circle where a step is almost a straight line. Segments, yeah. Segments of straight lines. Yeah. We can easily get the direction from the compass, but compass is not accurate enough. So we are actually she's looking at the gyrus compass, and to avoid any drifts that unwanted drifts that occurs because of magnetic interferences in the environment, by looking at the gyroscope, using the gyroscope and the compass. So because the gyroscope will not be influenced by the magnetic field, so we can fuse those two together to get a better magnetic heading. Yeah, actually, we have started looking at both the legs now. The correlation between the two legs, so that yeah. Right. Yeah.
It's able to detect non-signature because the way from remote.
Right. Thank you very much, then.
From there to here, what's perfect here?